we're going to go over the selecting indicators for acid-base titrations lab. This one should be kind of fun because you have your choice of indicators to use, and based on your calculations, you can decide which indicator you think would be the best for a particular titration. A lot of this early introductory information we've already talked about in quite a bit of detail in class, so I don't know that that this is really important for you to read. I mean, you're going to have to write your background, but you could almost do that again from the information that we've learned from the notes. But when you're titrating an acid with a base, you've got the curve on the left is going to be your general curve. And again, you can sort of tell this is a probably a weak acid, strong base titration here. And then the base titrated with acid is going to be the opposite of that. And then it's saying the steepness of the curve and the pH value at the equivalence point depend on the strength of the acid and the base. And we've already done a strong acid, strong base titration where the pH at the equivalence point is going to be 7. Okay. If you have a weak acid being titrated with a strong base, then the pH at the equivalence point is going to be greater than 7, which again we've already talked about that. And then they run through a bunch of these formulas here, and I feel like, you know, looking at all of this stuff, this is just kind of a don't worry about if you understand, just plug into these formulas we're giving you and you can get the answer. And that, I don't really like that. So again, maybe sort of ignore all of this, okay? Because I think you know how to make these calculations. We've been doing them in class, and I think this stuff does not promote the actual understanding of the material. So again, it's, you know, just talking about the way that the indicator works. Now this could be a little more useful, okay? Because with an indicator, it's basically talking about how if you've got the indicator, typically it's going to react in a certain way to change color, and this is explaining kind of how that works. So that might be a little bit different because we haven't really talked about how exactly an indicator works, so that could be some good stuff to read. It says the transition range for most indicators is about 2 pH units, which is usually okay because usually our curve is steep enough that doesn't make that much of a difference. Let's see here. Okay, and then it starts talking about how we're actually going to do the experiment. Okay, and so in our experiment here, we're doing a two titrations here. We're doing a weak acid with a strong base and a weak base with a strong acid. And so you'll get to practice graphing both of those curves, which is fun. So in part 1 of this lab, 25 milliliters of a 0.1 molar solution of a weak acid is titrated with a 0.1 molar solution of the strong base sodium hydroxide. Okay, and the Ka is 1.8 times 10 to the negative fifth. We want to calculate the pH at the equivalence point and enter this value in part 1 data table. Now, this is important that you do this. You know, it doesn't make a lot of difference that you're hearing this now. I'm going to tell you in class, you need to do this pre-lab before you actually start the lab. Otherwise, you're not going to know which indicator you need to use when you start the experiment. Okay? So this is actually, these pre-lab questions are actually very helpful in the lab itself. These are the actual volumes and the actual concentrations you're using in the lab. This is not theoretical. So we're using 25 milliliters of a 0.1 molar solution of acetic acid, and we're titrating with 0.1 molar solution of sodium hydroxide. Okay, and again, they're giving us the Ka for the acetic acid, so we need to figure out what's the pH at the equivalence point. Okay, so you have to remember what we talked about in class. At the equivalence point, the moles of the base are going to be equal to the moles of the acid. Okay, and we actually know sometimes with the titration, a lot of times we're going to have an unknown concentration of the weak acid or the weak base. This time we know the concentrations of both of these, so we're doing something different here. We're actually trying to select the best possible indicator for this lab. So that's why we are given both the concentrations here. But this actually makes this fairly easy, because if we are given both the concentrations, that means that I can figure out the concentration of the acetic, or the number of moles of acetic acid that we're initially reacting with here. So if you multiply this volume in liters by this concentration, then that's going to give you your number of moles of acetic acid. And actually, maybe we should write the equation that's going to happen here. I'm just going to have to write this over some of the text, and hopefully you can see it. CH3COOH, and we're adding the sodium hydroxide to that. The OH minus is the part of that that I care about, obviously. And because that's a strong base being added to a weak acid, this is going to go to completion. So we're going to end up with CH3COO minus plus H2O. Okay? And so CH3COO minus, that's acetate. Usually you probably see that as C2H3O2 minus, but that's another way to write it that's more, it shows the structure of it a little bit better. But basically what we're doing here is we are converting this weak acid into its conjugate base. Alright, so if we start initially here, and remember when we're doing stoichiometry we need to think in moles. So we're starting with 0.00250 moles of the acetic acid. At the equivalence point, we will have added 0.00250 moles of the hydroxide. Okay, so they don't tell us the volume of sodium hydroxide we need to add here, but at the equivalence point, that's how many moles we'll have. And I mean, you could probably look at this and tell we need to add 25 milliliters approximately to get to the equivalence point here. So once you have equal number of moles of both of those, then obviously these are going to react. And assuming that we don't have any of this in the solution to begin with, or it's negligible, this is going to go up by 0.00250. So then we end up with none of either of these, and then we end up with 0.00250 moles of the acetate ion at the end. Okay. So then, what we need to realize is that this acetate, after it's the only thing left in the solution with the water, it's going to start to do an equilibrium. Okay, and so the equilibrium that it's going to do, we have the CH3COO minus plus H2O, and that's going to change back into CH3COOH plus OH minus. Okay, and now it's doing an equilibrium. So if we think about concentrations here, because we're trying to figure out the pH of this solution at the equivalence point. Okay, and so our initial concentration here, we've now added 50 we should have 50 milliliters of this solution now, okay, because we would have to add 25 milliliters of the sodium hydroxide in order to get that to the equivalence point. So 50 milliliters of solution, so you take the 0.00250 divided by 0.050 for 50 milliliters, and our concentration here to start out with is 0.050 molar. And then we can assume none of this to begin with because all of that just got used up in our previous strong base reaction. So then this is going to go down by x, this is going to go up by x, and up by x. So we end up with 0.050 minus x, x, and x. And they gave us the Ka for acetic acid. Now in order to figure this out, we need to use the Kb for acetate. I'm going to erase this top one here so that I have room to do this. Keep the equilibrium one that we're working on right now. Okay, so the Kb, if you take 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th, then you get 5.6 times 10 to the negative 10th. So 5.6 times 10 to the negative 10th is equal to x squared. We plug this into our equilibrium expression over 0.050. And we're going to make our simplifying assumption here because that's a pretty small Kb, that x is fairly small. It's negligible compared to the 0.05 that we have. Then solve for x. X is going to give us our hydroxide concentration. So our x should be 5.3 times 10 to the negative 6 here. Okay, that's our OH minus concentration. So then if we take the negative log of that, that's going to give us our POH for this solution. Our POH should be about 5.28. That's a 5. So then our pH, we would have to take 14 minus that. And that would be about 8.72. Okay? I think we actually even calculated that in the notes for acetic acid. That's a fairly common one. So that's how you find the pH. Okay, so then once you figure out that the pH is going to be about 8.72 at the equivalence point, that's going to give you a good idea of what indicator you need to use for this particular titration, because you want an indicator that's going to change color around that pH. So if you look at the ranges here, the one that looks like it's going to change around the range that we need, and this didn't copy off very well, but this is kind of, these are the transition regions right here. So you can kind of see that on your sheet. Definitely can't see it very well on here. Okay, so the one that has the best transition range here is probably going to be the phenolphthalein, which is a little bit unfortunate because that's the indicator that we've used before. So, I mean, you're familiar with that one. It'd be nice to be able to use something different. But we'll get to for the next one. So this one is probably phenolphthalein's the best choice for that, okay? So once you figure all that out, which basically I just figured it out for you, then, okay, so it says to select the best indicator, so that's, the second part of number 1. And then at number 2, it says in part 2, 25 milliliters of a 0.1 molar solution of the weak base ammonia is titrated with 0.1 molar solution of the strong acid, hydrochloric acid, and then it gives you the Kb of ammonia. This is the exact same process as number 1, except reversed, because now we're titrating a weak base with a strong acid. Okay, so you can expect that the pH is going to be lower than 7. So you need to calculate the pH at the equivalence point. I'm not doing that one for you. You got to do something on your own here. And then select the appropriate indicator for that one. So you need to come into class on Monday knowing which indicators you're going to use for each part of this titration. Okay. And then number 3, 25 milliliters of a 0.1 molar solution of the weak acid HF is titrated with 0.1 molar solution of the weak base ammonia. Will the pH at the equivalence point be less than 7, equal to 7, or greater than 7? And explain. Okay. Now, a big hint on this one is that they're giving us the Ka for HF, and they're giving us the Kb for NH3. Okay? And so, basically what we have to figure out here is which one of these two is going to dissociate the most in solution. Okay? And you can probably already see which one is going to dissociate the most. Okay? And so this, when you titrate a weak acid with a weak base, which we're not really going to do that particular part of the lab, but they're just asking a good hypothetical question here. And actually, I've never really seen one like this on the AP exam either. I mean, they could hypothetically throw it in. We didn't really talk about it. But all you have to do here is just, compare the Ka and the Kb. All right? So the Ka for the HF is 7.2 times 10 to the negative 4th. The Kb for NH3 is 1.8 times 10 to the negative 5th. And they're not asking you to calculate exactly what the pH is. They just are asking conceptually, is it going to be less than 7, equal to 7, or greater than 7? I think you guys can figure that out based on the 2 Kas that are right there, and based on my hint that you need to be thinking about which one of these processes is going to happen to the greatest extent. Okay, that would give you an idea of whether we're going to have leftover H3O plus in this solution or leftover OH minus. Okay, So again, remember, just one more hint here in case you're having trouble with this. The NH3 is ultimately going to, in equilibrium, it's going to produce a little bit of OH minus, and the HF is going to produce a little bit of H plus. That OH minus and that H plus are going to react with one another to form water, but if one of them makes more of the ion than the other one, then you're going to have some leftover H plus or some leftover OH minus. You need to figure out which one you're going to have. Again, I probably did not need to explain that much. It's probably fairly obvious. All right, so there's your pre-lab. The lab itself, not too bad. I mean, basically, you're just being very careful with your volume measurements, and then you're doing a couple titrations. And we've done this already this year, so you should know the procedure. You've got a burette set up. Looks like this picture right here. The burette is draining either the strong acid or the strong base into the weak acid or weak base. And we're measuring the pH of that solution as it goes. Okay, and so again, you're gonna see that rapid rise in pH, and also if you have a good indicator, then you're gonna see the color change right around the equivalence point. You want to pick one that's going to change color so that your end point, which end point is when it changes color, is the same as your equivalence point. Okay, if you did a good job selecting the right indicator, then the color change is really going to be the best tool that you have to know when you have gotten to the equivalence point. Okay, but the data from your pH meter will help as well. So it tells you basically how to do this, how to do the titration, and you're going to be collecting data as you do it on these massive data tables here. Which again, we already did this earlier in the year where you're checking the burette reading, checking the pH, and they have an added thing here that tells indicator color. Okay, so you can note when the indicator changes color. You know, so I have to fill that out for all of them. But when the indicator does change color, that's where you'd want to mark that on your table. And then we're going to do it again for the second titration. And then really your only post-lab calculation and analysis here is making a couple graphs. So you're going to graph both of these titration curves, and it says indicate the indicator color for each data point. You do not need to do it for each data point, but just, you know, label that on your graph as far as your range. And then you can decide whether the indicators that were selected were appropriate for these two titrations. So the post-lab for this is not that bad. It's just a couple of graphs, and then you're done. All in all, not a bad lab. It's going to take us a couple days probably to get through the titrations. But hopefully that's fairly straightforward, and hopefully you can see how that connects to what we've been learning in class. So, all right, we'll see you in class.